Okay. So yeah, my assumption is you haven't done the exam yet. So what I'm going to do is I'm going to be going over some review questions just to kind of get the hang of it. So yesterday we went over the 4 quantum numbers, right? And then of course the last quantum number was the magnetic spin. And this is a quantum number that has only 2 values, positive 1/2 being the up spin, negative 1/2 being the down spin. Depending on how the questions are being asked, of course, you answer these questions accordingly. So let me see. There were some questions I had skipped over in the lesson. I wanted to make sure I went over that. This question right here is asking you the relationship between N and M sub L. So there's a relationship between the energy level and N sub L. So we're told here, now that I think about it, I think this is a typo because it says L and M sub L. This should be L, right? What values of M sub L are possible for L is equal to 2? So since I'm going over it right now, I don't need these words here. Remember that to figure out M sub L, you need to have the L value, because you will start for the M sub L, you will start from negative L, go all the way to 0, and then go all the way to positive L. So these are kind of the limits, right? Negative L is where you start. You add 1 each time, and it gives you all the possible M sub L values. So if L is 2, right, what do y'all think the M sub L value should be? At least, what's the first M sub L value when L is 2? It starts with negative what? Right. So yeah, you're starting with negative 2, right? And each time you're adding 1 until you end up at positive 2. So negative 2, when you add 1, you get negative 1. You add 1, you get 0. You add 1, you get positive 1. You add 1, you get positive 2, and then you check. Are you at positive L value? Yes, then you stop, right? Very good. So for this, you essentially are going to have 5 M sub L values. Remember, each M sub L value codes to 1 structure. So what you're saying here, or of course 1 orbital. So from the M sub L values, you can conclude that you're going to have 5 orbitals at this level, right? So yeah, at L is 2. L is 2 is technically the D block. So let me see. I had a bunch of periodic tables throughout here yesterday that I copied over. Was that in my? Oh, that was in my other class. Okay. Yeah, so L is 2 is actually the D block. So we can have that right here. So the D block, when you look at the D block, that's the green part here, the D block. And the way I try to visualize the M sub L's in the D block, I just group the elements in 2s, right? So I'm not going to draw on this first one because I have stuff in there. This is the first M sub L value, the negative 2. This is the next one. That's the negative 1, right? This is the next one. That's the 0. This is the next one. That's the plus 1. And this is the last one. That's the plus 2. So you can see here, you have 10 elements. But remember, 2 elements stay in 1 orbital because they are orbital mates. So 10 elements represents 10 electrons, and then 2 electrons in 1 orbital. So you have 10 electrons in the row of the D block, but you have 5 orbitals, right? 5 orbitals that can have a maximum collectively of 10 electrons. If you're being asked about, let's see, if you're being asked about the P sublevel, then let me draw this down here. You would have 1, 2, 3. With the P sublevel, L is 1, right? So your M sub L values will be negative 1. You start with negative L, 0, positive 1. So in the P sublevel, you have 3 possible structures. Of course, earlier we said these structures not only have numerical values, negative 1, 0, plus 1, they also have symbols, right? Px, Py, Pz. Negative 1, 0, plus 1. So there are 3 different variations of the p orbital. Then going back to the s orbital, let me use this down here so we can see. With the s orbital, you only have 1 type of s orbital. Since all the 3 axes go through the s orbital, this is just called s. You don't have the s sub x or s sub anything, just s, right? And so here we just have one m sub L value. Because the L is equal to 0, negative L is still 0, positive L is still 0, 0 is still 0, so we only have one m sub L value. So remember, when L is 0, the m sub L value is equal to 0. When L is 1, let me stick with the colors, the m sub L values are negative 1, 0, plus 1. When L is 2 right here, I guess I can write this right here for the D block. When L is 2, it's negative 2 for the m sub L, right? Negative 1, 0, plus 1, plus 2. So I use the periodic table to kind of remind me of what I should expect, right? And when it comes to this block down here, the F block, let me use brown color, why not? Let me see, I have 1, 2, 3, 4, 5, 6, 7, which is expected. Here we have the L is equal to 3. So though they're not asking you that, this is more like a review, right? Here we know L is 3. So if L is 3, then the possible m sub L values start from negative 3. This would be negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. Remember, this one here technically belongs up here. Okay? And so here's where you have all the different 7 flower shapes, right? So for the F orbital, you have 7 orbitals and then maximum 14 electrons. Okay, so we talked about this, of course, the 3 quantum numbers that code or describe the orbital, right? When they're saying describe the orbital, they kind of code to a very specific orbital, and in the process they're describing the energy levels, generic shape, specific orientation, right? So here we want to talk about the energy levels and the sublevels. I've used the term sublevel. So the energy level and sublevel, because I had a student ask me about this, actually a 1405 student, very, very insightful, deep thinker. She was trying to reconcile the energy level and the sublevel, right? So I'm not going to go too much into it. I'm just going to explain to you how they're related. In the energy level, it's easier to explain the energy level from the point of view of Bohr's model, because Bohr's model is still popular amongst non-chemistry folk just because it's a lot easier to explain. The quantum mechanical model is a little bit more challenging. It's more like a puzzle, and you require a lot of logic to kind of connect things together and all this stuff. Anyway, the idea here is, let's use Bohr's model or Bohr's idea of the energy level, and then we'll use the quantum mechanical model. Remember, the quantum mechanical model is more deeper. It's more like an improvement, a step up from Bohr's model. So in Bohr's model, I won't draw the whole planetary model. What I'll do is just draw the energy levels as lines. So imagine we're kind of zooming into one portion of the model, right? So what Bohr says, the energy levels are kind of like this. N is 1. And somebody asked me a question about this part here. Please notice that when you're looking at the energy levels, the gaps get smaller as you go higher in the energy level. So what I mean by that is I'm going to draw energy level 3. Oh, I don't want this to be so perfect. 3 right here, a lot closer. Okay. And then energy level 4 will be a little bit closer. And then energy level 5 will be even closer. The gaps get a lot closer to each other as you go high in energy level, right? So according to Bohr's model, the energy levels were in the orbits, they're perfect. There's no break between the energy level. But in the quantum mechanical model, by the way, his observations is the reason why scientists say his model works best for hydrogen only. Okay, because for hydrogen atom, this concept, this idea where the energy levels are just perfect and they're all, concentric circles, there's no breaks in the circles, this works for hydrogen. But when you come to elements that have more than one electron within the atom, things get complicated. All of a sudden, the energy levels start to break apart, right? Energy level 1 here pretty much has one level like that. Energy level 2, wait, let me try to keep it the same level so it's not as confusing. Energy level 2 actually breaks apart. So you have a small part that's actually in the S sublevel, another part that's in the P sublevel. So energy level 2 is now made up of, it breaks up in two. So a part of it moves slightly higher. Let me not make it that high because it's now going to bleed into the next one. But energy level 2 isn't so continuous anymore. It kind of breaks apart. And then the one part is what we call the S level. The other part is what we call the P level. There's only one energy level 1. And then when we get to energy level 3, that energy level breaks apart into 3 different segments. So what do you call these segments? These segments are called the sublevels. Okay? So this breaks up into S, into P, and into D. So S, P, D. While in Bohr's model, you just had one energy level. He never saw the S, never saw the P or the D shape, right? And then here when we get to 4, same thing. It got complicated. These energy levels that were supposed to be continuous now had segments. So these segments that the energy level breaks up into are what we call the sub-level. So imagine this is the before in their understanding. This is the after. So what a lot of books don't present this way. I feel like this is the best way of presenting it. So what I like to show you here once again is what used to be the same level energy is now broken up into what is called sub levels. So now the energy level 2 has a 2s sub level and 2p sub level. To get the whole energy level 2, you have to consider both 2s and 2p, if that makes sense, right? So now energy level 2 is made up of 2 sublevels, 2s and 2p. Together, 2s and 2p make up energy level 2. Energy level 3 is made up of 3 sublevels, 3s, 3p, 3d. So if you want to get all of energy level 3, you're technically adding the segments of energy level 3, 3s, 3p, 3d. So you can imagine 4 breaks up into 4 energy sublevels, right? So that's kind of the correlation here. And that's what this slide is explaining, right? What used to be a continuous smooth band according to Bohr, where he kind of oversimplified everything based on what he saw. Now we're seeing segments within the same energy level, and these are called the sub-levels. Sub is kind of like part of the whole, okay? So there's only, with the one energy level 1, it doesn't break apart into parts. Energy level 2, the same energy level breaks apart into 2 parts. Energy level 3 into 3. And of course, if they show you energy level 4, that will break up into 4, right? So that's the idea here, of course. We will continue with this concept some more in the next chapter 3, right? Yeah, we'll come back and look at this, but for right now, this is the relationship, right, between the two. Any questions about that concept? Okay, so of course here they're also showing you the M sub L values if you want to see that differently. You know, they're kind of giving you the summary. You have L is 0 for the S block, right? That's called the 1s orbital. M sub L is 0. For energy level 2, now energy level 2 has 2 sublevels, 2s, 2p, 2s. As long as the orbital is still in the S block, the M sub L is still 0, because you only have, and by the way, in this picture, each box represents the orbital. So that to me is like, imagine the architect drawing a picture, a schematic of a room that they're trying to build. Each box is like one room or one orbital, right? So each box here represents one orbital. Remember, each orbital can have a maximum of 2 electrons. So yeah, this little box here is one orbital, codes with M sub L 0. The p orbital, -1, 0 plus 1, just like we discussed, right? And then same here. No matter what the energy level is, as long as it's an s orbital, the M sub L will always be 0. As long as it's a p, M sub L will be -1, 0 plus 1. Okay? As long as it's a D, you have -2, -1, 0, +1, +2. Okay? Even at different energy levels. Okay, let's see. So now that I've explained that, we can continue with, oh, okay. So here they give you, let me try to see. Oh, over this too. Let me go over that too. So here we're answering this question here. What are the quantum numbers and names? For example, 2s. Okay, they want you to write the answer in this format. Oh, I told him. Okay, sorry, that's my brother. Yeah. For example, what are the quantum numbers and the names? So they want you to write it in the format 2s, 2p, right? So when they write 2s, remember the number 2, this is n, the energy level. And then s is the letter for the angular momentum or the azimuthal quantum number. Okay? So they want you to write your answer in this format, your first answer. All the orbitals in the n is equal to 4 principal level. So that's the first question. The second question you're going to be answering is how many n is equal to 4 orbitals actually exist? So what they do here is they write a lot of words, and I'm like, yeah, great. So let me do this. Let me add a page. I hope I can access the picture I posted yesterday. So let me see. I tried to... okay. Let me try to go to my other class because I got a picture yesterday. It's just a periodic table. This is my non-majors class. Oh, I have a lot of stuff on it. Yeah, I copied that, but I'm trying to see if I can use it in an uncomplicated form right now for us to review this. Now, this is a lot better. Yeah. So let me copy this and see if it allows me to do it cross classes. Ha. Okay, please work. Yes. Okay, right there. So now that I've come here, I forgot what I'm doing. Oh, we're answering this question here. N is 4. So let's go ahead, go through all the blocks. And I like this periodic table right here because it separates the blocks by color, right? And look at that. We have a little help right there. The sub-levels are labeled, right? So this is actually very helpful for us. Okay. So I don't have to work hard to identify the sub-levels because they literally labeled it for us. We'll go through anyway and find all the n is equal to 4 sub-levels in the different blocks. So once again, the light blue here, this is the S block. This is the P block where all the P orbitals are. This is the D block, and this is the F block, right? So I have to find all my energy level 4. They happen to have labeled it already, so it's so much easier for me. This is energy level 4 right here. Hopefully you can see that. That's 4S from the S block. Here, this right here is 4P, right? I mean, don't you like this periodic table? I like it. This wasn't around when I was in school. I'm like, why didn't somebody make this when I was in school? 4D right here, okay? And then 4F right here. Remember the energy level is the number. So you're just trying to find everywhere in the blocks where there is an energy level of 4. Remember, this is 1, 2, 3, all the way to 7, right? 4. And then you skip over the first level, 2, 3, 4. This is 3, 4, and this is 4, 5, right? We covered that before. Okay. So what I'm seeing here for the first question, write it in this form. I can write it that way. It's going to be 4S, 4P, right? 4D, and 4F. Because they said that write it that way in that format. The quantum numbers and the name in this format here. So I just went ahead and answered the first part. This part here got answered. The second part is asking you how many n is equal to 4 orbitals exist. Oh, now they want to know the orbitals, right? What they did down here is they did some math, and the math part thing works, I guess. 4 squared and they got 16. I like the whole visual thing, so let me do it the visual way. You can use the m sub l level way, because remember, each m sub l value codes to an orbital. So there's so many different ways you can answer this. I just like to go through here and count the elements, and essentially every 2 elements equal 1 orbital. So like, for example, potassium and calcium in the s block equal 1 orbital. So I'll say here that from 4s, I get 1 orbital. Okay, so let me move this over and say sublevels, number of orbitals. Okay, so in general, from 4s, you get 1 orbital. Okay, and then from 4p, once again, count in 2s, right? These 2 will room together in 1 orbital, gallium and germanium, Ga. Then right here, together, these together. So in the p sublevel, we get 3 orbitals. They didn't ask you for electrons. If they ask for electrons, each orbital has a maximum of 2 electrons, right? They're asking you for orbitals. Okay, what about the d? These 2 room together, these 2 room together, these 2 room together, those 2 room together, these 2 room together. So we have 1, 2, 3, 4, 5. This is 5 orbitals. Then with the f, I'm usually not very sure if we have the right number, so I like to count from the right. Okay, so here, there's always in pairs, right? So this is 1 orbital, 2 orbitals, 3 orbitals, 4 orbitals, 5 orbitals, 6 orbitals, 7 orbitals. This is actually written, this periodic table is a very good one. Okay, so 7 orbitals, 7. But they want to know total, right? I broke this up by sublevel. They want to know total. So number of orbitals for each is this. Now total. I'm going to use a calculator, y'all. I'm not even ashamed. 1 plus 3 plus 5 plus 7. Oh, you add all these up and you get 16 orbitals. You could have, oh, hold on a second, orbital. Oh, I'm writing too fast and I forgot how to spell. Yeah, so 16 orbitals, right? I like a more predictable way of figuring things out versus memorizing a formula. I'm not great at memorizing, because if I forget one thing, then I obsess over it. So I like this way the most. It gives me more peace when I'm working on stuff, because it's tangible, right? Who doesn't get a periodic table? In every exam you work on, you get a periodic table, except for the online exams here, because you have access to your periodic table, right? Whichever you choose to use. So the way they worked it out, they actually use the m sub l values, and if you go through here and count all of these individually, you should get 16. There's also a formula which says that if you have the value of n, the energy level you're looking at, if you square it, you get a number of orbitals. Okay? So you can go ahead and memorize that. Once again, me personally, I would not go with that, because if I forget one thing, then I just panic. I would rather count them and go with the logic. Okay? Any questions about that? So yeah, here's a summary of the formulas that you can use to remember. It's just a memory thing, so feel free. The number of sublevels within the energy level is n. The number of orbitals within the sublevel is this. I'd just rather count them, right? The number of orbitals within the level is this. Once again, for me, I mean, I got the counting thing down, right? The memorizing this, I look at it, I'm like, that's a lot of effort. I know, I should have a better attitude. Okay, so if you need to, it's right here available to you. Okay, so we did see all of this before, right? We saw all of this before. We talked about all of that. Now, so I won't go into all that, because as you can see, we have writings on it. This is the f orbital, and of course, this is a summary chart that shows you all the different shapes, all the different orbitals. I mean, imagine what Bohr saw in his time. all he saw was this, and he kept seeing the different S's at all the different energy levels, and he's thinking, wow, I've seen the whole atom. And then the group of scientists come behind him like, no, dude, you missed all of this right here. You missed all of this. But such is the world of science. Okay. Does anybody have any questions before I go off into the review stuff? Okay. So let me see, right? If you're thinking of something, just keep thinking. I can easily switch. Let me try to go to mastering chemistry because it's a little bit tricky. I'm trying to go to your textbook. Oh, wait. Yeah, I'm trying to go to the textbook. There it is. So I don't know if you guys are aware of this. It's a lot easier when you have a tangible textbook to find the resources in the textbook. But in your textbook, this used to be part of the homework or in the homework site on Pearson. But in your textbook, at the end of each chapter, there's some review questions. And since most of your questions are coming from a test bank, that was put together by the same textbook people. Here we are at something called the self-assessment quiz. Let me show you how to get to that. Okay, so your first exam, oh wow, it's been a long time, huh? Let's start with the easiest thing right now. We just finished chapter chapter 2. So let me go to chapter 2 right here, the quantum mechanical model of the atom. That's this one here. So yeah, self-assessment quiz. So if you click on that, you have to click on this again here to see the quiz, and then the quiz populates. So of course they ask you which wavelength of light has the highest frequency. So here you want to ask yourself, what is the frequency wavelength relationship? So as you're going through this is what I would do when I was a student. I would work on the problems in the back of the book, and I'm assuming if the author took the time to publish that problem, that means that the concept is important, right? Besides that, I skipped over an option that said summary. When they summarized the chapters, I wanted to make sure I knew stuff that was summarized in the chapter. If it was part of the learning objective and it was summarized and it was in questions, then that was definitely stuff I had to know, right? So here you ask which wavelength of light has the highest frequency. So this question isn't really that simple because you have nanometers, millimeters, nanometers, millimeters. So you want to know the general relationship between frequency and wavelength. Of course, they're inversely related, right? The higher the frequency, the smaller the wavelength. So you want to find the smallest wavelength, and then of course that will be your highest frequency. That's the first part, the relationship between frequency and wavelength. The other part is the value of the prefixes. These answers don't have the same units. You have answer choice, at least on my end, 1 and 3 being nanometers. So nanometers is a smaller, nano is a smaller metric prefix, right? So these number 2 and number 4 answer choices are much larger in value, in magnitude than number 1 and 3. So your answer is probably 1 or 3. Which one do y'all think your answer is for highest frequency? I have to go back here because I can't read. What do y'all think? Like which of these two is a much smaller wavelength, which will then give a higher frequency, because wavelength and frequency are inversely proportional. So if the wavelength is very small, the frequency is very high. That just means the waves are very tight. So the way I think about it, I try to have what I call walking knowledge, where you have a general understanding of something to where you can give somebody an answer without pulling up a reference, right? In my head, I visualize waves like hair textures. I know it's very weird, but if the wavelength is very big, you have a very loose curl texture. If the wavelength is very small, you have a very tight curl structure. And so if the wavelength is very small, you have a very tight curl structure. So you have a lot of curls in a small space. And the lot of curls translate into waves. and therefore you have a higher frequency of waves. Does that make sense at all? It makes sense in my head, right? I understand curls and I understand frequency, so I kind of relate the two to each other, right? Anyway, so between 10 nanometers and 1 nanometer, which one do you think is smaller? Anybody? Okay, let's try 1 nanometer. Let's see. Yay! Okay, there. So yeah, they remind you, right? So let's say you got it wrong. You did this, and it's as you're guessing through here, say you don't have time to go through everything. As you're guessing through here, they tell you what to remember, like what relationship to look at. Wavelength and frequency are inversely related. The shorter the wavelength, the greater the frequency. So you're looking for the shortest wavelengths. And of course, even when you get it right, they give you the logic that produce the right answer. So when you're studying, you want to follow the same pattern, because chemistry is all about patterns, right? If you see them do it, you do what they're doing. So even when you get the answer right, you're not done. You have to know why you got it right. And that helps you to improve your processes in chemistry, right? Yeah, so you go through all of these, the kind of radiations that contain the greatest energy per photon, just the greatest energy, right? Which of these waves is the most energetic and therefore the most damaging, right? I usually think about the gamma rays, the one that produce Hulk. Microwaves, they're dangerous enough, but not that dangerous. Not as much as the gamma rays, right? So you go there and they tell you again. They tell you what figure to look at. So you can go through. We didn't do energy per photon, so you can skip over number 3. If we didn't cover it, you can look at the PowerPoint. If we didn't cover it, skip over it. But you can go through here and then work a bunch of these. Oh, let's do number 6, because this relates more to what we just worked on, right? Which set of 3 quantum numbers does not specify an orbital in the hydrogen atom? Now, I mentioned this earlier that if you have a question like this, what you're looking for is which of these do not work, right? Because it says which of the 3 set of quantum numbers do not specify an orbital. If you know the restrictions in your head, it makes it a lot easier. If you don't worry about it. Just try to find a periodic table like I did. Let me find mine. And then see if these quantum numbers work. Okay, so let me, oh, where's my pencil? I just had it right here. I'm cleaning up my periodic table. Give me a moment. Okay, so I'm going to write my set of quantum numbers, because when I flip from one page to another, I can't see this page right here. So we'll work this out on the other page. So let me see. Oh, does somebody already have an answer? The last one? Okay, hold on. Yes, that's what I was heading towards, the last one. So let me show you why it doesn't work, right? Oops. Hold on just a second. N is equal to 3, L is equal to 3, M sub L is equal to negative 2. Okay, very good. So let me show you why it doesn't work. So when you go to N is 3, N is 3 is here. 1, 2, 3. This is N is 3 right here. 1, 2, 3. N is 3 right here. Technically, you can skip over the first one. N is 3 right here, 2, right? This is N is 3. And then N is 3 right. Oh, no, there's no N is 3 here, right, on the F block. Okay. So we gotten all the N is 3. Now let's find, it has to be N is 3 and L is 3. Now, this is L is 0. This is L is 1. This is L is 2. This is L is 3. But we just said there was no N is 3 when you are at L is 3. For that reason, this is not correct. For L is 3, we only have N is equal to 4 and N is equal to 5. We don't have any of the other N's here. Okay? So yeah, the last one is the one that doesn't work. Any questions about that? So if you have, once again, the quantum number thing memorized, then you can go through that. But yeah, you can go through all of these and kind of get an idea. Oh, let's do this last one here, this easier one. Which figure represents the d orbital? What do y'all think? See, the questions, I mean, not all the questions are bad. Some of them do require a little bit more thought, but not all of them do. As far as the balloons or the numbers of spheres are concerned, this is S, right? One sphere, two spheres, P, double of that, and then 4, double of this is going to be D. So that would be the D, right? Anyway, this is what I have for this. So do y'all have any other questions about the other chapters? Let me kind of skim, since we're here, let me skim over the other ones real quick. E-text, back to e-text. So that was number 2. Number 1 is atoms. We're going to do the ones that don't require a lot of calculations, right? Atoms, there. See where it says chapter review and summary? That's what I'm skipping over, but then that will pretty much tell you what you need to make sure you know, right? Okay, now we're working on this one here. Oh, sorry. Okay, there. Oh, look at that. This one here. Chapter 1, atoms. This is a simple one to do. We can do number 1. Okay. So I'm going to take a step back, and I'm going to have you guys let me know what you think it is, right? Says this image represents a particular view of a sample of matter. Classify the sample according to its composition. I think we worked on a worksheet, I think, yeah, that had a structure like this. So what do you all think this is? Let me see the answer choices. First of all, we have a sample. This sample is a compound. It is a heterogeneous mixture, a homogeneous mixture. This sample is a pure element. So we have to eliminate the erroneous answers, right? Which answer do you think is completely wrong? Or if you think you know the right answer, which answer do you think makes sense? Oh, by the way, when it comes to the images, make sure you try to kind of zoom in a little bit if you can zoom in, or pay attention to the images to make sure the size of the atoms are similar. You know, with this one here, because we have color, I would say it's a lot easier to tell. You have blue circles attached to white circles, and each of these each of these structures is the same, right? I was about to give some information away. I don't want to give it up just yet. Any ideas on what each of these units, structures, formulas represent? Are we looking at an element or a compound? What do y'all think? I was about to give some information away. I'm trying not to give information away. Okay. So the clue I'll give you is you have 2 units attached together that are not the same. When you have 2 units attached together to make a bigger unit, what do we call that? Oh, sorry. I usually hear thud whenever you, yeah, exactly, a compound, right. I hear some kind of alert. Am I in the wrong quiz? Let me close this one out. Yes, so this is a compound because the atoms, yeah, the different atoms are attached together to make a compound, and you have the exact same compound over and over and over again. There is no mixture here, because if there was a mixture, we'd have 2 different looking compounds, or maybe elements. The shape will look different. All we have here is the same shape with different orientations, right? So answer choice 2 and 3 is completely out. We said it was a compound because the colors are different. If the colors were the same, it would be an element. So compound it is. Okay, we didn't go over the theory, hypothesis, and that. So, two samples of a compound containing elements A and B are decomposed. The first sample produces 15 grams of A and 35 grams of B. The second sample produces 25 grams of A and what mass of B? So this question looks like one of those kind of mass ratio kind of questions. So what I want to do, even though I'm looking at this one here, what I would like to do, I think, instead, is work on number 4. A compound containing only carbon and hydrogen has a carbon to hydrogen mass ratio, right? Because this actually uses the term mass ratio. This one doesn't. It kind of, yeah. So almost a little bit scared of using the term mass ratio. So you have a compound containing carbon and hydrogen only that has a carbon to hydrogen mass ratio of 11.89. Which carbon to hydrogen mass ratio is possible for another compound composed of only of carbon and hydrogen? Wow, this is an interesting question. So we have a compound here. Okay, hold on. Let me add a page towards the end because I refuse to pull up the other area or the other chapter. Okay, so it says we have a compound containing carbon and hydrogen. So I'm writing on my iPad, and I'll pull this up in a second. See, I got some water on my iPad. Carbon and hydrogen, right? And the carbon to hydrogen, so the carbon over hydrogen mass ratio is 11.89. So if you take the mass of, that means the mass of carbon over mass of hydrogen give you 11.89. And they're asking you which carbon to hydrogen mass ratio is possible for another compound. So if you have a different compound, okay, that's important there. So another carbon and hydrogen compound that is composed of carbon and hydrogen. So which one is possible? Okay, this is a long way around describing the law of multiple proportion. So in the law, let me pull this up before, I'll come back to this right here real quick. In the law of multiple proportions, I'm just paraphrasing the law. If carbon and hydrogen, let me say, can form more than one compound, in this context here, two compounds, the mass ratios can be divided to form a whole number. So the mass ratios are related in a whole number fashion. So we have the mass ratio of the compound that we know. We don't really know the actual chemical formula, but we know this mass ratio here. So you kind of want to test this mass ratio against the other mass ratios until you get a whole number, because that's the requirement. So take this mass ratio here, divided by the other mass ratios, and once you get a whole number, then that other mass ratio is the one that's possible, because the goal here is dividing the two mass ratios will give you a whole number. Okay, so this is one of those questions where you're just kind of testing your way into the answer. Let me see. So let me write this here. I'm going to take 11.89 divide by 3.97, 11.89 divide by 7.89, 11.89 divided by 2.50, 11.89 divided by 4.66. And then we'll see which one gives us. So this is what I have written down. As soon as I get the whole number, I stop, right? 11.89 divided by 3.97. Okay, I get 2.99. So that may be my answer, right? It's very close. Let me try the next one. 11.89 divided by 7.89. 1.5. Definitely not very close to a whole number. 11.89 divided by 2.5. 4.8. Not close to a whole number. 11.89 divided by 4.66. 2.55. Whoo! That was doable. So the number that I get that's closest to a whole number will be this one. So I hope that works. The logic here is that mass ratios have to be a whole number, a small whole number, right? So you can go through all of this, right? We didn't do anything this specific with Millikan's oil drop experiment, but yeah, you can go through here. Rutherford's gold foil experiment. You can skip over number 6. We didn't go over that. Oh, let's do number 7. How many protons and neutrons are in the isotope Fe58? So Fe-58, that's our isotope, right? It's written in a different form. We want it to be written in this form for it to make sense, but they want to know number of protons and number of neutrons. So once again, I'm just skimming. I'm not going to go over every question, just skimming over a few. So what we're missing here, you want to convert this format into the symbolic one that we're more familiar with, the atomic symbol format. So for this, you need the periodic table. Your periodic table, find iron, and then you're looking for the atomic number. So that will be Fe. I'm going to write it as 58 right here for this isotope. I just write the mass number on top, and then the atomic number 26 on the bottom. I was missing that. Okay, this was missing. So I found this in the periodic table. Now I know a number of protons is the same thing as atomic number, so that will be 26, right? Number of neutrons is the difference between the mass number. Remember, this is a mass number, and this is protons plus neutrons. So what is this? 58 minus 26, 32, right? The difference between these two. Yeah. So when you have the atomic symbol in the proper form, it makes it easier. Just remember, when you're given the isotope, they're focusing on giving you the new mass that you can't find in the periodic table. That's the purpose of them writing it this way, right? But you have to use that mass because you're still dealing with the isotope, not the atomic symbol in the periodic table that gives you the average mass. We want the specific mass of the isotope that's being discussed, okay? Does anybody have any questions about what I'm talking about? Okay. Once again, if you have questions, just write it. I'll keep looking occasionally just to make sure. Don't feel bad about interrupting me. Okay. So what we worked on here, of course, is very similar to this one here, only they wrote the symbol differently, right? Giving you more information. And then I guess we can, let me see what else we can do here. I'm trying to figure out greatest number of atoms. Oh, haha. Oh, okay. So as I'm looking over this, I'm trying to decide what do I really want to work on. Okay, so let's see. I'm going to give you guys a choice here between 13, 14, and 15. I'm going to work one because I want to move on and look at chapter E. Which one do y'all want me to work on? I'm going to let you guys choose versus me choosing everything, right? Since all of these questions at some point involve atoms, we have to do the conversion that involves atoms. You let me know which one you want me to work on. And that will be the last one in this section. Of course, I'll go ahead and work on the rest. So you have 13, 14, 15. All these questions involve atoms, atoms, atoms. So at some point in our conversion, we're going to get to atoms. So let me know. Do you want me to work on 13? Do you want me to work on 14 or 15? Okay, so I heard somebody make a choice. 15? Okay, you have spoken. Now here's the good news about these. Let me select just an answer. Okay, I just randomly picked something and they're telling you incorrect. So they kind of show you what to do, how to do it. Let me click, because I'm not working on this, right? I'm just going to go through. Oh, even when I do get the correct choice here, they show you how to work it out. So you're not really missing out on much because I'm not working on that, right? Okay, good choice. Number 15. Let me write this out and then we'll see. Number 15. A 20.0 gram sample of elements contains 4.95 5 times 10 power 23 atoms. So I'm trying to identify elements, right? Okay. Let me go ahead and pull up my iPad, and then we'll go from there. Okay, so I have my information. I have grams, samples, and I have atoms. So the saying identify element. Now, before I start doing all my work, because, as a person who is working this out, I'm thinking, wait, they didn't give me the unit of my answer. That makes me a little anxious because I'm like, I usually rely heavily on the unit. Normally, we identify atoms by their number of protons. But there is no math that we're doing here with these starting numbers that will give me the protons. So if protons is not the first thing I'm looking for here based on the numbers given, the next best thing is molar mass, right? When we identify an element, most of the time, it's through protons if they give you the atomic symbol. But since you have mass and atoms, the next best thing is what is wanted here is molar mass. Molar mass or atomic mass. You know what I'm talking about? The mass of the element. So how do I know I'm looking for molar mass? Because of the units given to me. What is the symbol of the molar, not symbol, sorry, the unit of the molar mass? Molar mass, as far as periodic table is concerned, is usually given to you in 2 units. Either atomic mass unit, when you're doing that whole percent of the element, the abundance and stuff like that. In this context here, though, the molar mass is grams per mole. So for our problem, this is the more useful unit. AMU is not useful here because we use AMU for isotopes. Okay? Yeah, this is chemistry, y'all. Right. So knowing the units of the numbers you're looking for makes a difference. So if I know my target number is grams per mole, now I'm like, okay, I know what I'm looking for. Just need to take my grams, divide by moles, and that gives me the answer. I will use my molar mass then to find the element in the periodic table. So once I get grams for moles, grams divided by moles, I will use this to find element in periodic table. Okay, now I have a goal. So I look at my numbers given and I already have grams. I have my superscript number, right? But I have atoms and I want to convert atoms to moles. Remember I told you guys this a long time ago. It seems like a very long time. Every time you have atoms, you always think about atoms, moles. They kind of go together like yin and yang, right? So we had 2 molar conversions. 1 mole is equal to, for the most part, that usually is the atomic mass in grams of the element, or 1 mole is equal to Avogadro's number, 6 point. I just blanked out. What is Avogadro's number? Hold on, I have my conversions here. Like I was in the roll, but I just forgot what Avogadro's number was. 6.022 times 10 power 23 atoms. Since we're dealing with an element, I have to use atoms. If we're dealing with a compound, I would have to use the word molecule, right? Okay, there. Whew. That's why I have all these resources for when I blank out, right? Now, I don't know what the element is. So obviously this conversion is not useful because I cannot figure out the atomic mass, right? But my goal right here, goal number 1 or sub goal number 1 is to convert atoms to moles. So I take the number they gave me here, this number, okay. So I start with that number, and I use Avogadro's number, right? So I have a number of atoms. I have to put this number here, 6.022 times 10 power 23 atoms on the bottom, and I put 1 mole of whatever the compound, or whatever the element is. I have no idea what it is. I'll put 1 mole up here, work this out, and this will give me the amount of the elements in moles, right? Don't forget to use parentheses. Very important. When you're putting this in calculations, use parentheses so that your calculator doesn't separate these into two different numbers, okay? So open bracket 4.95 exponent 23 to the right, close brackets, divided by open, well, parentheses, 6.022 exponent 23 to the right, close that. And I get my answer as 7.3979 moles, okay? So I want to make sure my numbers look right. Oh, something here looks off. Oh, I think I pressed the wrong thing. Hold on, let me double check this number. 4.95 exponent 23. I think I pressed the wrong key here. To the right, close parentheses, divided by, open parentheses, 6.022 exponent 23 to the right, close parentheses. Okay, that looks a lot better because I was like, my number looks weird. Yeah, I pressed 9 when I was supposed to close the parentheses. You have to make sure you're pressing the right key. The light is not on here, and I have stick fingers. 0.821 moles. Right. Now that we have our moles, take your gram divided by mole. That's what molar mass is, right? So essentially, mass over moles equal molar mass. So I have my mass. My mole here is 0.821, right, mole. My mass is from up here, which is supposed to be what, 20.0? And that should give me my molar mass. So 20.0 divided by my molar mass should give me 24.33 grams per mole. So I go find my periodic table, which I have right here. Does the periodic table I have up here have molar mass in it? I don't even remember. Because it was a sub-level periodic table, right? No, it just had atomic number. Okay. No, it doesn't. Okay. So 24.3 on my end is magnesium. So yeah, 24.3 molar mass is magnesium. Let me check and see if that's an answer. Oh, it's the first one. I hope this is the right answer. Please work out. Oh, yay. There it is. They worked it out differently. Oh no, they didn't even work it out differently. Sorry. They didn't even work it out to get the whole answer. This is the number of moles here, right? Yeah, they got the same number of moles I got, 0.821. But this is a different question. This is that one. Do y'all see that? Oh, it's a typo. Anyway, yeah, magnesium, because I got 24.3 grams. Let me see if I can minimize, if I can have these side by side. Is it possible? Yeah, there. Because I got 24.33, magnesium symbol for me is 24.305 and an atomic number of 12. So that's the closest to this number here. Okay. Okay. Yeah, this one here is a typo. Something happened to where this copied over here. This has nothing to do with, this is not, we don't even know what the element here is. I mean, well, we didn't know it when we're working it out, so it shouldn't be mercury, right? Okay. So let me go back to this right here. X out of this. E. I'm trying to end on E as far as the review is concerned. This is a brief review, not like a super review or anything. Just skimming over and then kind of letting you guys know that we do have those options available. The self-assessment quiz. It will not count against you. It's not tied into the grade book at all, so don't worry about getting things wrong. Oh, so see, you have simple questions here from Fahrenheit to Kelvin. Don't forget, I do have that conversion sheet posted in one of the folders, right? That you want to know how to convert temperature scales from one to the other. Here, you're being told to express in millimeters. Let's see, what else is there? significant figures. Man, this is taking me back to the beginning. Look at that right here. Okay, I'm trying to skim over this and see which one do I want to work on. Okay, let me start with, I won't do the simple one here. I want to do the more complex one. Let's do number 3. How many significant figures are there in the number 0.0? Okay, right here. Add a page. So we have, maybe I can do this side by side. 0.080320, right? Of course, these numbers here are leading numbers, so they're not significant. And then for the significant numbers, 8 counts, 3 counts, 2 counts. Since the 0 is sandwiched between 2 non-zero numbers, it's also significant. And this 0 is after, if you look at this last 0 here, it's significant because to its left you have a 0, and to its left you have a decimal point. So all of these highlighted numbers here are significant, right? So that makes it 1, 2, 3, 4, 5. It should be 5. Let me check and see. Okay. Oh, I think we should work this number out. Let's work this one out. With this one here, yeah, all of these numbers pretty much are similar except for the number of significant figures. So it's very important to know the rules as you're working this out. So we have 43 for number 4, 0.998 times 0.00552, and then this whole thing is in parentheses, divide by 2.002, right? So this is one of those questions where, let me see, you have 1, 2, 3, 4, 5. You have 5 significant figures here. This is the one that requires PIMDAS because you have a mixture of operations, right? Here you have 1, 2, 3, 3 significant figures, and here you have 1, 2, 3, 4, 4 significant figures. Start with the numbers in the parentheses, right? Multiply them out first. So you have open parentheses, 43.998, close parentheses. Oh, well, let me get rid of the close parentheses. Multiply by 0.00552. So dark in here. Okay. So when I multiply my top numbers, I end up with 0.242. The good thing about this question is since we have all these numbers where that look very similar, right? Except for significant figures, I can go ahead and round this up early on. So this is 0.242, which I will write as 0.242. I'm supposed to round up to here, right, to 3 significant figures. But the number after this is 86. Record of that is supposed to be rounded down to 3 significant figures. Divide that by 2.004 significant figures. So ultimately, you can keep going, but your final answer should have 3 sig figs. Your final answer should have the same number of sig figs as the smallest sig figs in the numbers you're dividing, right? So I'll keep going. Divide by 2.002. My answer is 0.1213. My answer has to be rounded up or down to 3 sig figs. So this doesn't count. This stays. This stays. This one drops off, right? So I'm thinking it's this last one. Yeah, that last one. So you want to go through, do the same thing with this. We've done all of these before, something like that before. I'm trying to see what else I'm going to go over. Okay, so, okay, looking at the time. So what I'm going to do here is, let me do number 7. And then number 10 will be the last one. Number 7. I don't remember what questions are on the exam. I'm just trying to do the ones I feel like are very important to learn while we're in this class. Number 7, convert. So we're converting 1285 centimeters squared, 2 meters squared. If you look at your conversion sheet, we don't have length squared to length squared. The base unit here is a length. So you want to look at the length section of your conversion, right? And I have my sheet right here. And in my sheet, I see that 1 meter is equal to 100 centimeter. That's the conversion I see, or the equality I see in my length conversion. But the conversion here has the squared version of these. So you want to go ahead. I'll say the easiest, most efficient way, convert your converter to be the form you want it to be. So go ahead and square everything. So I'll say square this. When I say everything, I mean everything except for the equal sign, okay? So take 1 squared, m squared, equal 100 squared centimeters squared. Square your conversion to make it in the form that you need. Oops, I realized some parts are out of the frame. Right there, okay? So converter useful to you. So this ends up being 1 squared is 1. Meter squared remains as meter squared. 100 squared is 100 squared is 10,000, right? And then centimeters squared. So we finally took our unit that was, or our converter or equality that was in the simple length form, and we made it in a more useful form to us, which is now length squared, the length unit squared. So now you can convert. 1285. That's a comma, right? I have to make sure. Centimeters squared. Now we can use our conversion factor in the proper form. I put my 10,000 down here, my 1 meter squared up here, and then take my numbers. So I got my 185 divided by 10,000. And I get 0.1285 meters squared. This unit and this unit cancels out, and we're good. Oh, sorry. Yeah, so you see that, right? And so of all our answer choices, it looks like it's this one here. So that's the fun thing about chemistry. I call it fun now. Back then I was like, seriously? Why do we have units in the form that is not very useful to us? Why do we have to convert units when they're converters? So convert the converter until you get it in the form you need it to be in, and then use it, right? There. Now, some people like to write it this way, okay? The caveat. When I first started teaching, I used to teach it this way, but I started realizing that students will forget to square the number, or they'll forget to square the unit, and they'll keep going on, and then they'll mess up, right? If you write it this way, the way they have it in this calculation form, don't forget the square here, you're squaring both the number and the unit. That's why I found out the students who were working out this way. See, I learned a lot from you guys because my goal is to teach you the efficient way that helps you get it right, right? It's not about my process, it's about the process. In my head, there's such a thing as the process that kind of is most efficient. So when I watch students work things out, I try to figure out which way leads to more mistakes and which way leads to more answers. So I even adapt my teaching to go with that, okay? So when I started teaching, I used to go with this one here because that's how the textbook showed it. But I learned that more students did better with this method than that method. So just FYI. Oh, yeah. So let me go back here. This is my last one, y'all. Last one, number 10. See, I use up most of the time here. That's okay. Number 10. A German automobile gas mileage is 22 kilometers. So this is the mileage for number 10. 22 kilometers per liter. And I like to write this in the fractional form, right? Convert this to miles per gallon. So we're going to convert this to miles per gallon. Okay. And then we'll come back and try to find our answer. Okay, so let me highlight Since we have a fractional form of units, I like to split the units up into their base measurements, right? The type of measurements. Kilometers is the length, and so is miles. Okay. So when we're trying to convert this, we'll find the converter or the equality, the conversion factor in the length. So before I move on, let me go to my length section. So I do have my conversion factor here. I'm not going to pull it up because of time. We've done all this before, right? I'm going to my length. Can I find kilometers and miles? Oh, there it is. I see 1 kilometer equal 0.621 miles. Okay. Okay. So that works with my length conversion. Now I'm going to look at my other conversion here. Let me use my volume conversion, liter to gallons, right? This is the denominator unit, liters to gallons. For liters to gallons, let me see, liters to gallons. Oh, volume. I just said volume. Volume, liters and gallons, liters and gallons. Oh, I see it right there, liters and gallons. So for liters and gallons, I see 1 gallon equals 3.785 liters, right? So now I can tell I have all the conversions I need because I have the conversions that will convert from kilometers to miles and then gallons from liters, right? Now all I have to do is set it up. 22 kilometers on top, numerator position. Denominator position is liter. Now, if the unit by itself makes you nervous, feel free to put a 1 there. It doesn't change the value, right? So 22 kilometers over 1 liter is the same thing. I'm going to mix things up and convert the denominator first. To get rid of liters on the bottom, I have to place some number with the unit liters on top. That's how dimension analysis works. That means I'm using this conversion factor because only that one has liters, right? 3.785 liters. This will cancel out that, but this goes with 1 gallon, right? So I just use this conversion factor here. Okay, so I'm kind of half done because you see the gallon is where it needs to be on the bottom. Now I have to get the miles where it needs to be on the top. Okay, right now on top I have kilometers over gallon. Got to get rid of kilometers. Since kilometers is the numerator position, I need kilometer on the bottom to get rid of that kilometer, right? This is now the next unit I use, the next conversion factor. 1 kilometer, 0.621. Is it 0.621? Yeah, miles. Kilometer cancels out. 0.621 miles. Okay, so the units I have remaining now are mile on top, gallons on the bottom. I'm to the point where if the units don't work out, I'm not even wasting my time doing the math, right? Because the math is going to come out wrong if the units don't work out right. So I have miles on top, gallons on the bottom. Now I'll not waste my time, sorry. Now I'll invest my time doing the math. 22 times 3.785 times 0.621. Oh, that's it. 51.7. How many sig figs do I have? I didn't pay attention, did I? Okay, this is 2 sig figs. 1, 2, 3, 4. 4 sig figs. 1, 2, 3. 3 sig figs. So 2 should be the smallest, right? So this is miles per, just MI, miles per gallon. So you round this up to 52 miles per gallon. Okay, let me see. Oh, once again, out of frame. Let me see what they have here. Oh, yeah. Since they only gave us, I just remember something. Since they only gave us 1 number, my bad. I'm rushing a little bit. Since they only gave us 1 number, we go with the number significant figure, not the converters. Okay, I'm getting alerts for emails and that's distracting me. I do apologize, but yeah. So this one, okay. So as far as that is concerned, this is the answer. Any questions about this? Oh, sorry, you said something here. That was earlier, right? Do y'all have any questions about what I've been working on so far? I know it's been a while since we did chapter E, but go ahead, review those. You can watch the videos and stuff, but I think you should be ready to do your exam. Do you want to start with chapter 3 or you just want to wait till next week? Let me see what we have next. Oh, my coworkers are blasting my email. Yeah, let's see. Oh, okay. Give me just a moment. We should be able to do common ion test. Okay. So the common ion test, let's see. Yeah. Okay. I mean, we'll be a little behind, but I think we should be sort of fine. It's just with us missing all of last week, it makes it a little bit tricky, Because right now I just literally have 8 minutes left. So it's okay, guys. Well, what I'll try to do instead is maybe try to have a makeup day next week. So instead of just meeting for 2 days, we might meet for 3 to make sure that we are caught up with chapter 3. I think it'll be a lot better that way. And then, yeah, we can go from there because I don't really have that much time left. And when there's a lot of email blasts, that means something is going on that I have to address. So does anybody have any questions? Okay, if not, all the best, guys. Yeah, tomorrow we'll be in all these sessions, all these meetings. So teachers will sort of be unavailable. And I can tell the emails have already started tomorrow and Friday. But you can still shoot me an email. I can multitask. It's okay if I'm distracted in those meetings because I don't usually do the presentation, right? So it's okay. I can always email you when I'm in a meeting. I'll be like, okay, I'm in a meeting right now. But okay, I'll see you guys next week. Have a nice weekend.